Hello there and welcome to Radioactivity Part 2, a WAHEY Productions productive video. I'm Connor Durkin.
And I'm Will Carne, and welcome to WAHEY.
WAHEY.
Yes, it's brilliant.
This video should contain everything you need for an A star, but as always, please feel free to ask away in the comments section or complaint section as we're now referring to it.
Yes, you could compliment us, it would be lovely.
Compliment section, that's
compliment
much better.
section.
Compliment.
Right.
Compliment, because it goes along with the video.
Radioactive decay theory.
Everyone loves radioactive decay theory. As we said, radioactive decay is unpredictable, and every nucleus of the isotope has an equal probability of undergoing decay in a given time interval.
Yeah, we said that last video.
We did.
The isotope X with N0 nuclei, where N is the number of nuclei left in time T after the start.
Or just point out that N0 is not no, so it doesn't have no nuclei, it has N0 number of nuclei. See, you say that, but I thought that for the first time.
In time delta T, the number of nuclei that disintegrate is delta N, which is proportional to N and delta T.
So basically, delta N equals minus
lambda.
Lambda, that's the one. Minus lambda multiplied by N multiplied by delta T, where lambda is the decay constant. As delta N is always decreasing, there is a minus.
Therefore, the rate of disintegration, delta N over delta T, or for mathematicians, dN over dt, equals minus lambda N.
Now, the rate of disintegration is just the activity. So the activity A equals lambda N. Rather simple, really.
Now, if you integrate that, you get N equals N0 e to the power of minus lambda T. And because mass is proportional to the number of nuclei, you get the same equation if you use M.
Also, activity will follow the same equation as will count rate, found with a Geiger tube. So they're all linked.
Yeah, they're all that basic equation. Now, E is just the exponential function, or for non-mathsy people, a constant, 2.718.
And so on and so on. Lambda, the decay constant, is a probability of an individual nucleus decaying per second.
You can relate the half-life to your half with a bit of maths. It's so quick, I'll show you. Actually, we might as well, shall we? Yeah. The number of nuclei, n at time t, when t equals 0, is n0.
Therefore, at time t equals t a half, n will equal half n0.
Sub this into the earlier equation, and then the n0's cancel out, leaving you with 0.5 equals e to the minus lambda t a half.
It's lovely stuff. Yeah. Natural log both sides, or ln both sides, and you get ln 0.5 equals minus lambda t to the power of
ln
half.
Yeah, and 0.5 is just 2 to the power of minus 1, cheeky log rules, and voila! In ln 2 over lambda equals t. It's a half-life.
It's most simple. It'll be on the thing.
Somewhere. It is. Yeah. It's so simple.
It's also good to make note that n equals 0.5 to the power n multiplied by n0.
Yeah, where the little n is the number of half-lives. Yes. That just might come in handy. Maybe. Okay, let's speed this along a bit. We're going a bit slowly. Useful radioactive isotopes.
Living organisms contain a small amount of carbon-14, a radioactive isotope of carbon made in the atmosphere by adding a neutron to nitrogen.
Yes, as you can see the equation.
On the board. Okay,
yes.
Lovely. Its half-life is 5,570 years, so you can date an organism by looking at the ratio of carbon-14 left in it. As the decay is proportional to the number of atoms, you can get a measure to the current activity to date the sample.
Another form of dating is potassium-40, which decays by electron capture to get argon gas, which gets trapped in rocks.
It also decays with beta-minus decay to get calcium-40, which is 8 times more likely to occur than electron capture.
The half-life of potassium-40 is 1,250 million years.
Oh.
So by measuring the proportion of argon-40 to potassium-40, you can age the rock sample.
Lovely. If for every n potassium-40 there is 1 argon-40, there must have been n plus 9 potassium-40 originally.
Yeah. Therefore, the n and the e equation, you can determine the age of the sample.
A radioactive tracer is used to measure or follow the path of a substance through a system. It should
have a half-life stable enough for measurements to be made, short enough to decay quickly after use.
Emit beta or gamma radiation, so it can be detected outside the flow path.
Examples of this are underground pipe leaks, modelling oil reservoirs, the uptake of fertilisers by plants, and the uptake of iodine by the thyroid gland.
Some medical stuff. Moving on to useful radioactive isotopes. Plenty of them.
Yes, a useful way to see nuclear stability is to plot a graph of neutron number n against proton number z.
From z is 0 until about z is 20, the stability curve will follow the line n equals z.
Then above 20, stable nuclei have more neutrons than protons.
The extra neutrons help bind the nucleons together.
Alpha emitters occur beyond around z equals 60-ish, and note at around 80 protons you get about 120 neutrons.
Above 120, the nuclei are too large to be able to be stable, hence the end of the line, so things start decaying very quickly.
Yes, the strong nuclear force is unable to overcome the electrostatic repulsion.
Beta-minus emitters occur above the line with neutron-rich nuclei, and beta-plus emitters occur below with proton-rich nuclei. Proton neutrons, yeah.
Electron capture also takes place here, down under there, as it's very similar to in basically, as beta plus emission.
In terms of what it produces. So you can see the effect of decays on N and Z with a graph like this as zoomed-in version of the main graph. Look at it. Look at it.
You may have to draw a graph similar to this to represent the decay of an element. Think of it just as the graphical method of working out the equation.
Lovely stuff. You can tell what decay a particle will undergo by its position on the main graph.
In a series of radioactive decays, you can predict its path by its movement towards the line of stability.
You can make beta minus emitters by bombarding a stable isotope with neutrons, or beta plus by bombarding it with protons.
However, when using protons, they have to have sufficient kinetic energy to overcome the repulsion from the nucleus.
After a nucleus emits an alpha or beta particle, or undergoes electron capture, it might emit a gamma photon, which allows the nucleus to lose energy and conservation of energy.
This will happen if the daughter nucleus is in an excited state.
Very excited. I'm so excited. Copyright.
The nucleus will soon move to its ground state, either directly or by other states.
So it's got different pathways. These can be represented in an energy level diagram. The example shown is magnesium decaying to aluminium.
Yes, you also need to know the application in medicine of technetium-99, which emits only...
Technetium.
Technetium, what did I say?
Tectinium?
Why did I say that?
Because you're mental. Technetium-99, which emits only gamma radiation. It can be used as a tracer to show tissue or organ function. It has a half-life of only 6 hours, decaying into a more stable isotope very quickly.
Yes. Now, earlier, we did an experiment on... We didn't do an experiment, we said an experiment.
Well, not as far as the government's concerned, we didn't.
On the radius of a nucleus, but now onto a far more accurate experiment to do with electron diffraction.
Electron diffraction. This involves firing a beam of high-energy electrons at a thin solid sample of an element.
The electrons are diffracted by the nucleus because the de Broglie wavelength is about the same as the diameter of the nucleus. Electrons don't experience the strong nuclear force, so you get more accurate measurements.
If you are confused, it's de Broglie as his French pronunciation, but de Broglie is really
I like de Broglie.
It's de Broglie. Everyone knows it's de Broglie. When directed onto a thin film of material in front of a screen, interference causes, because electron wave particle duality, blah blah. Wave particle duality for electrons.
Interference causes diffraction pattern to be seen. On the screen, similar to the light patterns you saw in the AS.
Using measurements from this pattern, you can measure the size and spacing of the material's atomic nuclei.
Be careful, this is not the same as electron diffraction at AS, where you have gaps. This involves high-energy electrons diffracted by individual
nuclei. Be careful,
nuclei.
you lot. The major difference is that electrons are diffracted, not repelled by the nuclei, so the intensity decreases as the angle increases.
It's been shown that the radius of the nucleides, R, depends on the mass number, A, with R equals R naught A to the power of the third, where R naught is a constant of 1.05 femtometers.
Lovely. Using this, you can gain the graphs of ln R against ln A, where R0 will be the intercept of the gradient, and the gradient will be a third.
Yeah. R against A to the power of a third, which should go through the origin with a gradient R naught cubed.
And R cubed against A, where again the line goes to the origin with a gradient of R0.
A bit of simple maths will show you how to get this information using the classic y equals mx plus c.
Classic.
Now these graphs can therefore be used to find the values at R naught.
A final one we haven't shown is R against A, which will be a parabola from the origin because it's a third powers graph. It's bleh.
Yeah.
It's rubbish.
Then assuming the nucleus is spherical, its volume will be given by V equals 4/3 pi R cubed.
Which equals 4/3 pi multiplied by R naught A to the power of a third, and then R naught and A to the power of a third is in a bracket, and then that bracket is cubed.
Yeah, that's just the formula we had a little bit earlier, which equals 4/3 pi R naught cubed A.
Therefore, V is proportional to its atomic mass A.
Now, you should know by now that the density is mass divided by volume, and here the mass is AU, where U is 1.661 times 10 to the minus 27, or just the atomic mass unit.
Indeed. Therefore, density is AU divided by 4/3 pi R naught cubed A. The A's cancel out, leaving U over 4/3 pi R naught cubed, which is just
3U over 4 pi R naught cubed, which, if you must know, is about 3.4 times 10 to the 17 kilograms per meters cubed.
Lovely stuff. Therefore, using... it says beautiful here, but I'm going to go for...
It's beautiful.
It's average.
The density of the nuclei is constant, so nucleons are separated by the same distance, regardless of their size. That's pretty good.
It's pretty amazing, actually. It's amazing, as Brian Cox would say. As nuclear density is much larger than atomic density, most of an atom's mass is in its nucleus. The nucleus is small compared to the atom, and therefore the atom must contain mostly empty space.
I am a scientist.
I think someone I read likened it to two or three flies floating around inside a cathedral. That's the sort of scale we're talking about.
Cathedral?
It's ridiculous. And cathedral, yeah.
Anyway.
A big cathedral.
Anyway, thank you for listening. This has been part B. Join us next time as we do nuclear energy.
I've been Connor Durkin.
I've been Will Carne.
Have any questions, please don't be afraid to ask in the comments. Goodbye.